Let's take a look at infinite geometric series. There's lots of different infinite series that go on forever and ever, but a lot of them are kind of boring for us. The ones that are interesting are going to be the geometric ones. First of all, I want to take a look at partial sums, and that's just the sum of n terms of an infinite series. So here we have this infinite series. It starts at a half, and we're multiplying by half every time, so this is geometric. If I want to find S1, that would be the first partial sum. That's just the sum of the first term. If we want to find S2, then we would add together two terms. So a half plus a quarter is 3/4. S3 would be the sum of the first three terms. So the 3/4 plus another eighth makes 7/8. And what we can do is start looking at a whole list of partial sums and see what might happen. And just after looking at the first six partial sums, we kind of see where this is heading. If we want to find the sum of infinitely many terms, which we just label as S, it looks like each of these fractions is getting closer and closer to 1. Now, if we try that with this geometric series, the first partial sum is 3. The second one is 3 plus 6, or 9. Then we get 21. 21 plus 24 is 45. What's happening with all of these terms, they're just getting bigger and bigger and bigger. And actually, when I add the fifth number to it, that's going to be an even bigger number that I'm going to add onto this pile. And that as we continue this, this infinite sum is just going to get bigger and bigger and bigger. Now, what causes that? Well, when we looked at this example, notice that our common ratio was 1/2. We kept multiplying by half every time. And so the amount that we added was half of the amount that we added last time. So as we continue on down the list, we're adding half of that amount, and then half of that amount, and half of that amount, and it's just getting smaller and smaller and smaller. Now, for this example, the common ratio is 2. For each consecutive or successive number, the term is getting bigger and bigger and bigger. So we added some, and then I added twice that amount to the pile, and then I add twice that amount to the pile. So that's why this sum gets bigger and bigger and bigger. So let's take a look at our formula for the sum of a geometric series. Now, what we just saw is that if the common ratio is greater than 1, and I mean that in absolute value, if the common ratio is greater than 1, then that infinite sum is going to be infinity. But what happens if the common ratio is less than 1? So we have that common ratio, it's a fraction, and that's what makes each successive term smaller and smaller. Well, the thing is, if we're dealing with a fraction, and we let this power get bigger and bigger and bigger, then the whole exponent, I mean, for example, take 1/2 to the 100th power, or 1/2 to the 1,000th power. I mean, you do that on your calculator, you start getting a very small number. And if we actually go way out close to infinity, this number right here turns into 0. And so as far as my equation goes, we're going to be taking this A1 times basically 0. So our sum of an infinite series is just going to be A1 over 1 minus R. Write this down. This is the sum of an infinite series. The important thing to remember about this, though, is that this only works if R is less than 1. Okay? If our common ratio is bigger than 1, then our infinite sum is going to be infinity. So let's find a couple. First of all, whenever we have a list, we should be checking out, is this arithmetic or geometric? And each time we're multiplying by the same number. I keep multiplying by -3/4. And so to get from -3/4 to 9/16, I multiply again by -3/4. So that's what my common ratio is going to be. Since that common ratio is less than 1, we can find the infinite sum. And all we do is take that first term, put it on top. In the denominator, we go 1 minus the common ratio. And here, our common ratio is -3/4. So that's 1 over 1 plus 3/4. 1 over 7/4. So our infinite sum is going to be 4/7. If we see it written in sigma notation, what we should always do with sigma notation is start writing out terms. So if I plug 1 in there, I'll get 5 times 0.8, which is 4. Then I'll get 5 times 0.8 to the second power, which is 3.2. And as I keep going, we'll get 2.56, 2.048, and so on. And this is, it is geometric. You can see it already looks like it's geometric because there's our A1 times r to the n. And our r is 0.8, which is smaller than 1. So we can go ahead and find this sum of this series by starting with our first number, which is 4, over 1 minus the common ratio, which we said is 0.8. So just a little bit of arithmetic. 4 divided by 0.2 is 20. And that's how we find the sum of an infinite series. Remembering our formula right here. And then using it.